We'll call this crystal NCA because Tesla dopes their nickel, or N, with a dash of cobalt and aluminum, Ca. All the differences we'll explore today between LFP and NCA result from the difference in these two crystal structures. And what do we see? In LFP, the lithium is the gray spheres, the phosphate is the red triangles, and the iron is the blue octahedra. The lithium is stored in one-dimensional, or 1D, tubes with the red triangles of the phosphates forming the walls and the blue octahedra of the iron forming the floors and ceilings. These tubes restrict the movement of lithium ions because they can only enter and exit the tubes one at a time, which slows down the rate that the tubes can be emptied and filled. The process of entering and exiting the tubes is called diffusion. That is, LFP has a slow diffusion rate. With that said, the walls, ceilings, and floors of the crystal structure also have a benefit. They keep the crystal structure from collapsing when the lithium ions leave and result in a crystal structure that's more chemically stable. One thing that's not obvious from the image of the crystal structure is that LFP is a poor electrical conductor. Why is this? In the center of each blue octahedron is an iron atom. There are oxygen atoms at each corner of the octahedron that put extra distance between the iron atoms. In order for iron to conduct electricity, each iron atom has to be within 3 angstroms of the next iron atom. The oxygen atoms at the corners of the blue octahedra force the iron atoms to 4 angstroms apart. An angstrom is just a measure of length at the atomic scale. The point is that the iron atoms can't conduct electricity with each other because they're spaced too far apart. And, in order for a lithium-ion battery to work, the cathode has to conduct electricity to and from the gray lithium ions using the cathode crystal as an electrical network. As a quick summary of LFP, it has a strong crystal structure, but that crystal structure is poor at conducting electricity to and from the lithium ions. Additionally, the lithium ions are contained in 1D tubes which slow down the diffusion rate of the ions. However, manufacturers of LFP batteries have mostly solved the issues with electrical conductivity and ionic traffic jams in 3 ways. First, LFP batteries often use LFP cathode particles less than 1/10 of a micron in diameter compared to the 10-micron particles often used in NCA batteries. That is, LFP crystals are 100 times smaller than NCA crystals. Reducing the particle size of LFP increases surface area, which helps solve the ionic traffic jam problem by creating more entry and exit points for a given volume of LFP crystals. Second, carbon coatings have been developed that increase the surface conductivity of the LFP particles, which drastically increases the conductivity between LFP particles. As we can see here, carbon coatings increase the initial battery capacity by about 50%, from 80 mAh per gram to 120 mAh per gram. Third, dopants such as magnesium have been used to increase the conductivity within the LFP crystal, not just the surface. This raises the capacity from about 120 mAh per gram to about 160 mAh per gram. By comparison, NCA has around 200 mAh per gram of usable capacity. In other words, in terms of the amount of lithium that LFP can store, it's only about 20% less than an NCA chemistry. If that's the case, why does a typical NCA battery cell achieve 250 watt-hours per kilogram, and a typical LFP battery cell achieve 160 watt-hours per kilogram, which is 36% less rather than 20% less? It's due to voltage. Watts are calculated by multiplying volts by amps. LFP has an average voltage of 3.2 volts, whereas NCA has an average voltage of 3.7 volts, or 14% less. That is, a 14% energy density difference due to voltage and a 20% difference due to lithium capacity gets us close to the 36% gravimetric energy density difference between LFP and NCA at the cell level. There are other factors at play here, but this back-of-the-napkin calculation explains the two largest factors at play for the gravimetric energy density difference between the two chemistries. Gravimetric energy density means the amount of energy storage for a given weight of material, or watt-hours per kilogram. This is as opposed to volumetric energy density, which is energy storage for a given volume of material, or watt-hours per liter. We'll cover both gravimetric and volumetric energy density at the cell and pack level later in the video. Before we wrap up LFP, there's one more note regarding voltage. LFP has an extraordinarily flat voltage profile. As the battery charges and discharges, the voltage range is confined to 3.1 to 3.3 volts for the majority of the cycle. Why is this? The voltage in a battery cell is dictated by the natural voltage potential between the cathode and anode. During charge and discharge, the chemical composition of both the cathode and anode change as lithium shifts between the cathode and anode. As the chemical composition changes, so does the voltage potential. The changes in chemical composition are called phase changes, and they appear as physical changes in the crystal structure of the cathode and anode. In NCA cathodes, the lithium ions are free to shuffle around in their 2D planes. As they shuffle around, the entire crystal structure changes continuously and in a unified way. That is, every part of the cathode crystal structure remains electrochemically active throughout the charge and discharge cycles. This results in the gradual slope we see in the charging profile of high nickel and high cobalt batteries. The entire crystal structure of the NCA and graphite are gradually changing, which shows up as a moderately steep but smooth slope. Let's contrast this with LFP. As lithium ions leave the 1D tubes in the LFP crystal, those parts of the crystal structure become electrochemically inactive. That is, the voltage potential of the cathode remains steady because the cathode continues to react from the active core, while the surface shuts down and remains chemically and structurally separate. This trick of maintaining two separate crystal structures within the same crystal is called a two-phase crystal structure. Let's do a quick summary for LFP and then move on to NCA. Out of the box, LFP has issues with conductivity and moving ions in and out of the crystal structure. This was solved by making the LFP particles smaller, adding a carbon coating, and doping it up with elements like magnesium. Without those innovations, LFP wouldn't have been commercially viable. Even with those innovations, LFP is outperformed at the cell level by NCA. The gravimetric energy density of LFP is lower than NCA by about 36% for cells like CATL is using. However, as we'll see, the higher stability of the LFP crystal structure results in a safer battery cell that requires less packaging. This means that at the pack level, LFP closes some of the performance gap with NCA. The two-phase crystal structure of LFP generates the flat voltage profile we see in LFP batteries. This flat voltage profile has some advantages for hardware and software engineers because it provides voltage and current that are more steady and less dynamic. However, it can also pose a challenge for vehicle manufacturers that are used to NCA-based battery cells. The state of charge of a battery is usually measured through voltage, and with such a narrow voltage profile, you can get wacky state of charge readings in cold weather. We'll come back to cold weather performance, but first we need to cover off NCA. In NCA, the lithium is the gray spheres again, and the NCA is orange. The lithium here is stored in two dimensions or planes, which we'll call slabs. The ions can enter and exit the crystal structure relatively freely because it doesn't have walls like LFP. This means a high lithium diffusion rate. As for electrical conductivity, the nickel atoms are tightly packed, and the NCA cathode material conducts electricity freely to and from the lithium ions. What's not to like? Well, the crystal structure is weak. As lithium is removed from the lithium slab, the crystal structure becomes weaker and more reactive. Even though the NCA crystal structure can hold quite a bit of lithium at 274 milliamp-hours per gram, the amount of lithium that can be safely removed limits that capacity to around 200 milliamp-hours per gram. Some of the lithium ions must remain in the NCA crystal structure to serve as pillars to hold up the nickel oxide slabs, which would collapse without the lithium. Furthermore, just like the blue iron octahedra had oxygen at each corner, the orange nickel octahedra also have oxygen at each corner. However, whereas the oxygen bonds in the LFP are strong, the oxygen bonds in the NCA are weak. This means NCA loses oxygen more easily, and oxygen is fuel for fire. While we're on the topic of safety, how do LFP and NCA compare? First, a quick primer on battery fires and thermal runaway. When a battery cell shorts out, all of the energy in the cell is released in a matter of seconds, generating heat. That heat drives side reactions that release oxygen, generating more heat, which drives more side reactions. This loop is called thermal runaway. NCA starts decomposing and releasing oxygen gas at around 150 Celsius. When it decomposes, it releases heat on the order of 940 joules per gram. The end result is an explosive reaction that culminates in a molten fireball. LFP, on the other hand, starts decomposing and releasing oxygen gas at 270 Celsius. When it decomposes, it only releases 200 joules per gram. This means thermal runaway is triggered at higher temperatures, it's less violent, and less oxygen is released. This leads to a hot battery that bursts but doesn't necessarily turn into a molten fireball. Let's do a quick recap of NCA before moving on to pack level performance. NCA is higher energy density than LFP because it stores more lithium and has a higher voltage potential. The drawback of NCA is that it's less stable and results in battery cells that are susceptible to violent thermal runaway events. LFP cells, on the other hand, tend to burst and smoke. Still dangerous, but more benign. Now on to how the performance of LFP and NCA at the cell level translates to the pack level. Bear in mind that the numbers I'm about to provide here are estimates, or I've chosen a round number that's easy to work with and within a few % of actual. Some of the numbers simply weren't publicly available and I had to triangulate numbers based on multiple sources. Currently, NCA battery cells like Tesla's are above 250 watt-hours per kilogram, and LFP battery cells like CATL's are above 160 watt-hours per kilogram, or 36% less. As for volumetric energy density, NCA battery cells like Tesla's are around 720 watt-hours per liter, and LFP battery cells like CATL's are around 390 watt-hours per liter, or 45% less. At the pack level, NCA battery packs like Tesla's are around 163 watt-hours per kilogram, and LFP battery packs like CATL's are around 128 watt-hours per kilogram, or 21% less. As for volumetric energy density, NCA battery packs like Tesla's are around 238 watt-hours per liter, and LFP battery packs like CATL's are around 168 watt-hours per liter, or 30% less. That is, LFP is able to make up about 15% of its gravimetric and volumetric energy density shortcomings at the pack level. This is because it's a more durable chemistry and therefore requires less protection. Less protection means less additional weight and volume. People often wonder why Chinese battery producers almost always opt for a prismatic cell for their LFP battery chemistries. It's because large prismatic battery cells are rectangular and fill a rectangular pack better than cylindrical cells. This helps make up for the poor volumetric energy density of LFP. The volumetric energy density limitations are also why the LFP Standard Range Plus Model 3 is limited to 253 miles of range versus 262 for the NCA version. Furthermore, it's also why you can get an even larger NCA pack for the Model 3 long range that provides 353 miles of range, or 40% more range, in the same space as the 253-mile range LFP battery pack. Again, these are rough figures. Tesla might be able to pack more LFP cells into standard range Model 3s or more nickel cells into the long range. But the vast gap between LFP and NCA volumetric energy density would remain, and it would still limit how much energy you can pack under a Model 3 with LFP, and therefore limit its range. That is, watt-hours per kilogram is often used as the key metric for lithium-ion batteries, but with LFP, the most important figure is watt-hours per liter, followed closely by watt-hours per kilogram. Given that LFP battery packs have a lower gravimetric energy density than NCA, they'll be heavier. What does this mean for performance and handling? Let's use the Standard Range Plus LFP versus the NCA version as an example. The LFP battery pack results in a vehicle that's 125 kilograms heavier, resulting in an efficiency number that's about 5% less. Note that the pack size is about 1 kilowatt-hour larger than the LFP battery pack to make up for this, but the range is still 9 miles shorter due to the greater weight. The 0 to 60 times appear to be unaffected, but overall, the handling in the LFP Model 3 might feel slightly less agile, but not significantly less agile. The impact would be less than having one large person or two smaller people in the vehicle because the weight would be low slung in the battery pack, as well as evenly distributed. Furthermore, the Model 3 is designed to carry the long-range pack with dual motors, which are heavier than the LFP battery pack. So the Model 3 has the powertrain, suspension, and crash protection in place to deal with the extra weight. I've yet to see a track performance comparison of LFP versus NCA Model 3s to see how this plays out, but LFP will probably perform slightly worse due to the extra weight in comparison to an NCA pack. On that note, I'm not sure how the LFP battery will perform at the track after multiple laps. This will come down to factors such as the cooling system, which I've heard nothing about so far. But if you're buying a Model 3 for track runs, you'd probably get the Performance Model 3 instead. Consumers might see additional wear on things like tires and brakes, but this wouldn't have a drastic impact on total cost of ownership. Furthermore, as we'll see in a moment, the extra battery life of an LFP battery pack will more than make up for any additional brake and tire costs. What about fears of cold weather performance? The gray bars in this image show the performance of a high nickel chemistry similar to NCA from -20 Celsius to 60 Celsius. The blue bars show an LFP chemistry in a similar temperature range. As you can see, below 0 degrees, the nickel chemistry drastically outperforms LFP. The reason for this goes back to the 1D crystal structure of LFP we discussed earlier. The slow lithium diffusion between the electrolyte solution and the LFP crystal structure was solved at warmer temperatures by using nanoscale LFP particles. However, as the electrolyte solution gets colder, the lithium diffusion slows down and the 1D crystal structure again becomes a bottleneck. But there's an easy way around this. Warm up the pack. The red bars in this image show an LFP chemistry that's heated with an element to keep the pack warm in colder temperatures. The energy used in the heating element more than makes up for the energy used during the heating process and results in cold weather range that's similar to what would be expected in warmer temperatures. Teslas have a similar function called preconditioning. The catch is that preconditioning takes up to 45 minutes. But for most people, this isn't an issue because preconditioning can be scheduled through the Tesla app. It can also be done while the vehicle is plugged in to minimize any range loss. Last year and earlier this year, China-made Model 3s with LFP battery packs were showing strange readings and were having cold weather range issues. My guess is this is due to a combination of LFP's poor cold weather performance and the flat voltage profile. Regardless, Tesla pushed updates throughout the winter which appear to have resolved those issues. It's worth noting that all vehicles experience range loss in cold weather, and electric vehicles are no exception. This is mostly due to the extra energy used to heat the cabin, but also due to a number of minor factors like tire pressure, air density, and road grip. The takeaway here is that down to about 0 to 10 Celsius, LFP performs similar to an NCA battery. At 0 Celsius and below, LFP performance degrades rapidly, but it can be addressed with pack heating. However, at those temperatures, you'd probably preheat the cabin and the battery anyways. Lastly, the cold weather issues that the LFP packs and Model 3s were having appear to have been solved by software updates. The next point to cover about LFP versus NCA is cycle life. On average, LFP has a cycle life 3 to 4 times longer than NCA. This is for 2 reasons. First, as we discussed earlier, the crystal structure of LFP is physically and chemically more robust than NCA. Second, the voltage window of LFP is on average about 0.5 volts less than NCA. That doesn't sound like much, but it's enough to create a harsher chemical environment that degrades the battery cell. The benefit of long cycle life is obvious. An LFP battery pack with 253 miles of range should last up to 1,000,000 miles, possibly more. A not so obvious benefit of the long life is that range will degrade less quickly. By the time an NCA battery with a range of 262 miles hits end of life, which is 80% capacity, the range will be 210 miles. An LFP battery with 253 miles of range will only be half to a quarter of the way through its life at the same point that the NCA is end of life. This means that when the NCA battery hits 80% of range remaining and 210 miles of range, the LFP battery will have 90 to 95% of its range remaining with 230 to 240 miles of range. So, the LFP battery cell will actually have longer range than NCA for the majority of its useful life. The reason why LFP can be charged to 100% comfortably is for a slightly different reason than the long cycle life, but contributes to long cycle life. As we covered earlier, LFP is a two-phase structure where parts of the crystal, for lack of a better term, deactivate as the battery charges. This has a protective effect at 100% charge state when the crystal structure is empty. It's not invincible at 100% charge state, but LFP can certainly be charged to or kept at 100% charge state more frequently and with much less degradation than NCA. The 2D single-phase structure of NCA isn't as robust as the 1D two-phase crystal structure of LFP. As an NCA cell is charged and lithium is removed from the crystal structure, it becomes more unstable and reactive. Above about a 90 to 95% charge state, NCA becomes unstable enough that it begins releasing oxygen that degrades the battery, and at 100% charge, the electrolyte begins to oxidize. You can charge an NCA battery above 100% charge, but power electronics usually prevent this because it shortens the battery life, and the chemistry becomes highly reactive and dangerous. Next, charge rate. The charge rate of the made-in-China Model 3 Standard Range Plus with LFP is pretty much in line with the Standard Range Plus produced in Fremont with NCA. In the image on screen, LFP is in red and NCA is in green. We'll ignore the Model 3 in black because it's a newer vehicle with a newer cell chemistry and Tesla might still be dialing in the charge rate. Right out of the gates, the Fremont Model 3 accepts a higher charge rate. This is likely due to the silicon in the NCA battery cell. If you'd like to know more about why silicon can accept a higher charge rate, check out my silicon fast charge video. By 40% state of charge, LFP catches up to NCA, and above 75% state of charge, LFP accepts a higher charge rate. I'm not sure why the LFP performs so well above 75%, but I'm guessing that it's because the LFP cell contains more synthetic graphite. If you'd like to know more about synthetic versus natural graphite, check out my video by that name. Overall, below 40% state of charge, NCA is faster than LFP. Between 40 to 70% state of charge, LFP and NCA are neck and neck, and above 70% state of charge, LFP is faster. Bjorn Nyland's YouTube channel shows the real-time video results, and on screen is a snapshot of LFP versus NCA at the point that LFP hits a 90% charge state. As you can see, the NCA lags slightly behind, but they're comparable. So, regardless of which chemistry a customer chooses, charge rate probably won't be a big consideration. With regards to cost, that was covered in the last LFP video on LFP licensing. In short, LFP packs are about 20% cheaper if they're manufactured in the same country as the vehicle that they're installed in. If they're shipped from China to the US, for example, the cost savings would be minimal and might be break even. That is, don't expect price cuts with LFP, especially when Tesla has a 4 to 6 month order backlog. Closely related to cost is raw materials availability and scaling. Iron is about 100 times more abundant than nickel. This means that no matter how large the LFP battery industry scales or how quickly, iron will not become a bottleneck. Lithium may become a bottleneck at some point, but according to Benchmark Minerals, things are looking pretty good until the mid-2020s. But that might change given how quickly battery cell production plans are accelerating. Overall, there could be a number of raw materials that intermittently become the bottleneck for battery production, like copper, rare earths, and graphite. As always, this doesn't mean growth stops, but that either growth slows or the most efficient producers like Tesla and Chinese companies devour the supply chains of their competitors and sweep the table. In summary, for most people, based on the research I've done and the reports coming out so far, LFP batteries may be a better choice for most people. However, ultimately, it comes down to the needs of the specific buyer, availability of cells, and vehicle price. Personally, if I can, I'm going to get a Model 3 with LFP battery cells. This will come in especially handy if the robotaxi network comes online. That use case will put miles on the vehicle quickly, and I expect the LFP chemistry could at least triple service life at no additional cost. Rather than rehash all the key points in the video for this summary, I've made this image so you can compare and contrast LFP and NCA. Overall, NCA is more energy dense, but LFP has greater safety, longer cycle life, and greater raw materials availability. LFP does have some cold weather issues due to the slow lithium diffusion and flat voltage profile, but with battery preconditioning and software updates, these appear to be problems Tesla can work around. As Elon Musk has said, Tesla will switch all their standard range vehicles to LFP batteries. As an investor, I couldn't be happier about this. LFP will increase safety and reduce the risk of costly recalls. Furthermore, LFP is more scalable than nickel-based chemistries, and it's ideal for a subcompact Tesla Model Q, or whatever they end up calling it. With LFP battery packs, they should be able to pump out several million of these subcompact vehicles per year with a lot less stress than they would have with a nickel supply chain. I wouldn't be surprised if a subcompact Tesla ends up being the Toyota Corolla of the 21st century, which has sold 43 million vehicles since it started production in 1996. In the next